Good morning, everyone. My name is Eleonora Ricci and I'm going to present a work entitled Experimental Data for the Calibration of a Nonlinear Numerical Model for Describing the Response of Masonry Constructions under Cyclic Loadings. Starting from the motivation and the main objectives of the work, I'm going to describe the experimental investigation that we carried out, and after discussing the results, I'm going to present the numerical model that we developed in a finite element software called Abacus in order to reproduce the seismic response of the analyzed structure under cyclic loading. Recent seismic events have highlighted the need of deepening the knowledge of the seismic response of masonry structures in order to ensure the human safety and the preservation of the architectural and historical heritage. It has been observed that even though some earthquake-induced collapses have occurred, surviving masonry structures displayed signs of seismic response, which has not been fully explored, especially for masonry arches and bolts. In fact, while the static analysis of arches is widely investigated, a better understanding of the response of masonry bolts and arches under dynamic loading conditions is necessary for the evaluation of the behavior of the structural elements, especially when located in seismically active areas. A first step in this direction is the study of the structural response under cyclic loads. The seismic capacity of curved masonry structures can be estimated by limit analysis under the well-known Hyman's hypothesis that you see in the slide. A different problem is that of describing the whole structural behavior of these structures in seismic conditions. To this aim, numerical distinct element method or finite element method analysis have to be performed using a micro or a macro modeling approaches. This requires a careful calibration of the material models to satisfactorily reproduce the actual structural behavior. Therefore, some research efforts have focused on the experimental analysis of the static response of the masonry material under cyclic loadings, in order to deepen the knowledge on the hysteretic characteristics of the entire structure, and provide the mechanical parameters needed for the calibration of the aforementioned models used to predict the seismic behavior of masonry structures and their loading capacity. In this context, the present study is aimed at the experimental investigation of the cyclic behavior of curved masonry structures, which is essential in view of their dissipation capacity and the ductility of the structure. Starting from the experimental data, cohesive frictional interface damage models can be calibrated. These allow for the description of the nonlinear response of masonry constructions under cyclic loadings. An experimental test has been performed on a circular arch made of 15 blocks of Apulian tuff, whose geometrical dimensions are shown in this slide. The test has been conducted in displacement control and was performed by putting the arch under a steel frame used to support the loading device. The load was applied very slowly using an hydraulic jack with a maximum capacity of 500 kN fixed on the rigid contrast beam. Moreover, a load cell with a capacity of 5 kN has been put between the ball joint of the hydraulic jack and the arch. The concentrated vertical load, represented by a red arrow in the slide, was applied at about 1/4 of the span. During the test, the oil pressure in the hydraulic jet was constantly adjusted by a feedback system managed by a LabVIEW software in order to perform a displacement control test. This way, the load, measured by the load cell, was promptly adjusted in order to realize the desired target displacement. The very low speed of the test was fundamental in order to avoid undesired effects related to the use of an hydraulic instrument in applying the load. 6 LVDT displacement transducers were positioned on the arch as shown in the slide. Transducers number 1 and 2 were put on both sides of the voussoir number 10, where the load was applied, measuring vertical displacements. Transducers number 3 and 4 were put on a symmetrical position with respect to the load application point, to measure both horizontal and vertical displacements respectively. Transducers number 5 and 6 were used to monitor eventual vertical rigid displacements of the beam supporting the arch. The materials used for building the arch were mechanically characterized by 3-point bending tests on mortar samples and compression strength tests on tuff blocks. Moreover, shear tests on triplets were carried out with different levels of normal precompression, 0.1 megapascal, 0.2 and 0.3 megapascal, for calibrating the parameters of the Mohr-Coulomb failure criterion. 11 cycles were performed, increasing the load of about 100–200 Newton at each cycle. Notice that in the last 3 cycles we needed to lower the maximum load in order to avoid a catastrophic collapse of the arch. In the slide you can see the load values plotted against the displacement measured at the load application point. In particular, each cycle was marked with a different color, and the black dashed line marked the value of the collapse load estimated by the kinematic theorem of limit analysis, which is found to be equal to 995 Newton. The arch exhibited the classic 4 hinges mechanism. In particular, the first hinge, named H1, formed at the extrados between voussoirs number 10 and 9, near the load application point. The second hinge, H2, formed in a position symmetric to H1 at the intrados of the arch, between voussoirs number 4 and 5. The third hinge, H3, occurred at the extrados between the blocks number 2 and 3, while the fourth hinge, H4, occurred at the symmetrical position with respect to H3, between blocks number 13 and 14. In particular, the first joint openings have been observed during the cycle number 6, between blocks number 9 and 10 and blocks 4 and 5. During the cycle number 7, the opening of the joints between the voussoirs 9 and 10 and 4 and 5, corresponding to the opening of the first and second hinges, respectively, was again observed. Moreover, at a load of about 1,210 Newton, new fractures occurred between the voussoirs 2 and 3 and 13 and 14, perfectly symmetrical one another, which means that also the third and fourth hinge formed. In the cycle number 8, at a peak load of about 1,310 Newton, all 4 hinges were opened. The subsequent 3 load cycles, cycle number 9, 10 and 11, were characterized by a progressive reduction of the peak load, characterized by much more large displacements. Moreover, the residual displacement at the complete unloading increases even more in the last cycles. In cycle 11, after a peak load of about 1,090 Newton, in correspondence of a displacement of 3.33 millimeters, the test was pushed up to a displacement of about 6.2 millimeters, where a decrease of the sustained load up to 940 Newton was observed. In this slide, the stiffness values up to the cycle number 8 are plotted versus the residual displacement at the complete unloading. It can be noticed that for the first 2 cycles, the stiffness is practically the same, and that the residual displacement is negligible, while a sudden decrease of stiffness is noted at the cycle number 4, corresponding to a jump of the residual displacement from 0.01 to 0.03 millimeters. This behavior is probably due to the formation of some cracks at the joints that involves irreversible deformations and damage with decrease of the stiffness. It is likely that the cracks formed at the joints where the first and second hinges occurred, although at cycle number 4 these hinges are not still visible by eye. From cycle number 4 to cycle number 6, the residual displacement increases of additional 0.06 millimeters, while the stiffness remains almost the same. After the cycle number 6, the stiffness hardly decreases. This indicates the progression of the openings of the joints. The residual displacement reaches a value of 0.25 millimeters at the end of cycle number 8. The experimental data have been employed for calibrating a numerical model of the arch, developed in Abacus, capable of simulating the cyclic behavior observed in the test. We modeled separately masonry blocks as linear elastic and mortar joints, where all the nonlinearities were supposed to be concentrated. Mortar joints were described by the concrete damage plasticity. The behavior and compression was calibrated with reference to previous experimental studies performed by us on similar mortars. For what concerns the tensile behavior, a bilinear softening law was chosen for a more accurate description. The calibration of this law was performed starting by literature data on the fracture energy, with reference to the observed response of the arch. For the description of the damage, the same approach employed by Scacco et al. In 2020 was adopted. In this slide, the geometry of the model and the adopted mesh are displayed. For taking into account the damage parameter has been changed during the analysis, and every time the analysis has been restarted. Only the first 8 cycles have been simulated, leaving out further cycles characterized by a decrease of the maximum load. Simulations have been performed in displacement control. Here you can see an animation of the nonlinear analysis performed and the results in terms of displacement, load values, and also stiffness at the beginning and at the end of each cycle. In this slide, the comparison between the numerical and experimental results is displayed. In particular, the load displacement diagram of the envelope of the cyclic response is reported for the numerical model and the experimental test. Moreover, the stiffness and the loss of stiffness values are plotted for each of the first 8 cycles for the numerical model and the experimentally tested arch. As you can see, the numerical model gives slightly higher loads, while a good accuracy has been obtained in terms of stiffness and especially of loss of stiffness due to the damage. Considering that we employed a continuous finite element model developed by a commercial code, avoiding the complexity of using interfaces or distinct element model approach, the results are very interesting. Finally, for what concerns the location of hinges, in 3 cases the numerical model locates the hinge at the next joint with respect to the position of the experimentally observed hinge. This minor difference can be due to the slight slidings at the supports observed in the experimental test, which were prevented in the numerical model by the considered boundary conditions. In conclusion, an experimental investigation of a masonry arch under cyclic loads has been carried out in view of the modeling of the response of masonry structures embedding arches under seismic loadings. The key aspects of the experimentally observed behavior are the following. First, the stiffness is constant only for low loads and decreases with the formation of cracks in the mortar, rapidly approaching very low values in view of collapse. Second, masonry arches can sustain cyclic loadings even beyond the peak load, showing a very progressive softening phase without a marked loss of loading capacity. Third, the permanent displacements at the complete unloading are relatively low, and the hysteretic loops show a narrow shape, characterized by high displacement capacity but low dissipation. And finally, a relatively simple numerical model has been successfully calibrated for simulating the experimentally observed behavior. Thank you all for your attention.